Hello everyone, welcome to video lecture series on module 3 probability distributions of subject complex analysis, probability and statistical methods with subject code 18MAT41. In this video I am going to take one more discrete probability distribution type, Poisson distribution. In my last video I have taken binomial distribution. If suppose a random experiment which has only two possible outcomes, success and failure, we can classify them as success and failure for n times, then the probability of x success out of that n trial we can find by the probability function p of x is equal to ncx p power x q power n minus x. So that means the probability function here depends on two parameters, the total number of trial taken n and the probability of success p. And also we have taken that mean mu is equal to np, variance v is npq, standard deviation sigma, that is square root of variance, that is root npq. So now I take Poisson distribution, which is also a discrete probability distribution. Poisson distribution is a limiting case of binomial distribution for which we need to have n very large, totally the large number of trial we have to take in order to get occurrence of a success. So that means this is a limiting case of the binomial distribution by making n very large and p very small and keeping np a constant fixed, say np equal to m, then the distribution is called Poisson distribution. And this distribution is used to describe the behavior of rare events. So this is possible when we have a rare event. Suppose we are counting the number of occurrences of an event in a given unit of time, distance, area or volume. For example, the number of car accidents in a day, so number of a bad reaction out of a new vaccination, etc. So that means it describes the number of events occurring in a fixed time interval or region of opportunity. Now, so the probability distribution function p of x of a Poisson random variable x that represent the number of success occurring in a given time interval is nothing but we define the probability function p of x as m power x exponential minus m by x factorial, where x can be 0 to infinity. So the range for x is 0 to infinity and m means the mean number of success. So that means the probability function of Poisson distribution is depends on one parameter m, which is nothing but mean number of success. So the example we can take for Poisson distribution, the number of deaths by horse kicking in the army camp, birth defects and genetic mutations, number of typing errors on a page. So we can see here, so all these are the rare events. So it is possible if we take the number of trials more, but the probability of occurrence is very small. So that means n is tends to infinity and the p is negligibly small, means it is close to 0. So almost it is close to 0. So next, mean variance and standard deviation of Poisson distribution. For Poisson distribution, the mean is nothing but mu equal to m, which we have already taken while taking the probability function for Poisson distribution, that is m power x exponential minus m by x factorial, where m is nothing but mean of success. So variance v is also equal to m. Standard deviation sigma, that is square root of variance, means root m. So that means for Poisson distribution, mean and variance are same. Next we take problems on Poisson distribution. Problem number 1. The probability that an individual suffers a bad reaction from a certain injection is given 0.001. Determine the probability that out of 2000 individuals, exactly 3, more than 2 will suffer a bad reaction. So here we can observe n is very large, 2000 individuals. The sample space is 2000, out of which the probability of bad reaction from an injection is only 0.001, a small. So thereby I can say it follows a Poisson distribution. That is, given that P is 0.001 n 2000, since P is very small, so we can consider Poisson distribution. So for that probability function we need M. So M is nothing but mean of the Poisson distribution, which is nothing but NP. So we first find M, that is N into P, 2000 into 0.001, that is 2. So thereby probability function P of x m power x exponential minus m by x factorial now becomes 2 power x e power minus 2 by x factorial. Now we can find the probability out of 2000 individuals, exactly 3 will have a bad reaction. That is, just substituting x equal to 3, P of 3 is equal to 2 cube by e power minus 2 by 3 factorial. So that is 0.1804. Now we move on to the next, that is more than 2 will suffer a bad reaction. So that means probability of x greater than or equal to 3. If I take a direct way, that is 3 up to 2000, all those probabilities we have to add. Instead of that, we can take the complement of that, that is 1 minus p of x less than 3. Since it is a discrete, so we have only 3 values, that is 1 minus probability of 0 plus probability of 1 plus probability of 2. So since probability function here is 2 power x e power minus 2 by x factorial, so I can substitute x equal to 0, 1, 2 here. So I get 1 minus, when x is 0, that is 2 power 0 by 0 factorial 1 into e power minus 2. When x equal to 1, 2 power 1 by 1 factorial, that means 2 e power minus 2. When x equal to, we have 2 square by 2 factorial, that is 4 by 2, that is 2 e power minus 2. So it is simplifies to 1 minus 5 times e power minus 2, which is nothing but 0.3233. So that is the answer. Now the next problem I can take. It is known that the chance of an error in the transmission of a message through a communication channel is 0.002. 2000 messages are sent through the channel. Find the probability that at least 3 messages will be received incorrect. Similar type of problem. So here n is 2000, very large, and p, the probability of error in the transmission of a message is 0.002. So p is very small. So I have to consider Poisson distribution here also, with the probability function as usual m power x exponential minus m by x factorial, where m is, now we have to calculate, that is 2000 into 0.002 np, which is 4. So p of x is 4 power x e power minus m by, that is e power minus 4 by x factorial. Now I take probability at least 3 messages. So that means greater than or equal to 3. So the probability that at least 3 messages will be received incorrectly, that is probability of x greater than or equal to 3, means complement of x less than 3. So I have 1 minus p of 0 plus p of 1 plus p of 2. So substitute x equal to 0, 1, 2 in the probability function, that is 4 power x e power minus 4 by 0 x factorial, where x is 0 means it is e power minus 4. When x equal to 1, 4 power 1 by 1 factorial, that is 4 times exponential minus 4. When x equal to 2, that is 4 square by 2 factorial, that is 16 by 2, 8 times exponential minus 4. So it comes to be now 13 times exponential minus 4. 1 minus 13 times exponential minus 4 e power minus 4. So give it to calculator. It will give the answer 0.7619. Next problem. Problem number 3. A car hire firm has 2 cars which it hires out on a day-to-day basis. The number of demands for a car is known to be Poisson distribution with mean 1.5. So the mean is directly given by mentioning this follows a Poisson distribution. Find the probability of a day on which there is no demand for the car and the demand is rejected. So here the m is directly given, so we can take m 1.5, and probability function for Poisson, as you know, it is m power x e power minus m by x factorial, where m is 1.5. So that's why p of x is 1.5 power x exponential minus 1.5 by x factorial. So let me now take no demand. No demand means 0. So probability of x equal to 0. So the probability of day on which there is no demand for the car is P of 0. So which gives 1.5 power 0, that is 1 by 0 factorial 1. 1 into e power minus 1.5, which is nothing but 0.2231. Now what about the demand is rejected? So when will be the demand is rejected? The car firm has only 2 cars. If it exceeds more than 2, so that means greater than or equal to 3, that there is a demand for greater than or equal to 3, then obviously he has to reject, the firm has to reject the demand. So that's why the probability of a day on which the demand is rejected is nothing but finding the probability for x greater than or equal to 3. So that means it is 1 minus probability of x less than 3, complement of probability of x less than 3. So once again we have the same situation, 1 minus p of 0 plus p of 1 plus p of 2. Substitute here x equal to 0, 1, 2, we'll get that as e power minus 1.5 plus when x equal to 1, 1.5 power 1 by 1 factorial, that gives 1.5 times exponential minus 1.5, plus when x equal to 2, we'll get 1.5 square by 2 factorial, which simplifies to 1.125 times exponential minus 1.5. Sum it up, so we'll get, and subtract from 1 minus of this, give directly this to calculator, will get 0.1912 as the answer. Next, problem number 4. In a certain factory turning out razor blades, there is a small chance of 0.002 for any blade to be defective. The blades are supplied in packets of 10. Use Poisson distribution to calculate the approximate number of packets containing no defective, 1 defective and 2 defective blades respectively in a consignment of 10,000 packets. So here they have given the probability of defective blade, that is 0.002. That means a very small quantity, 1 in 500, and we need to find the approximate number of packets containing. So the packets here, the blades are supplied in packets of 10. That means n should be taken as 10. Now for Poisson distribution, I want m. So the probability function depends on parameter m. So I need to first calculate m. So P is given, that is probability of a defective blade is 1 by 500, 0.002. Now in a packet of 10, the mean number of defective blades is m. I can calculate with np. N is 10 into p is 0.002, which comes to be 0.02. So therefore I can write the probability function 0.02 power x exponential minus 0.02 by x factorial. Now here the problem is finding approximate number of packets containing no defective, 1 defective, 2 defective out of 10,000 packets. So that means I need an expected number. So I have to find expected number of packets containing no defective, means multiply 10,000 with the probability of x equal to 0. So 10,000 into p of 0 likewise. So let me now first take expected number of packets containing defective blades in 10,000 packets. So that means multiply p of x by 10,000. So denote it as f of x. So f of x means 10,000 into p of x. That is number of packets containing x defective blades in 10,000 packets. So which simplifies to, since e power minus 0.02 is 0.9802, multiply with 10,000, that gives 9,802 times 0.02 power x by x factorial. So now I can go for each, that is no defective means x takes 0. So the number of packets containing no defective out of 10,000 packets means f of 0. So if I substitute, that gives 9,802 into 1, since 0.02 power 0 by 0 factorial is 1, so we'll get 9,802. So what about the next one? Number of packets containing 1 defective, f of 1. 9,802 times 0.02 power 1 by 1 factorial. So which is nothing but now 9,802 times 0.02, that is 196. The last one is number of packets containing 2 defective, that is f of 2. So that gives 9,802 times 0.02 square by 2 factorial, which simplifies to 1.96. So since it is number of packets, so we have to round it to the nearest integer value, so that is 2. Next, problem number 5. The probability that a news reader commits no mistake in reading the news is 1 by e power 3. Find the probability that on a particular news broadcast he commits only 2 mistakes, more than 3 mistakes, at most 3 mistakes. So here the probability that a newsreader commits no mistake is given. So that means P of 0 is given, which is nothing but e power minus 3. So now since it is the probability is in terms of exponential, so I can have a hint that it follows a Poisson distribution. Now in order to find the probabilities under Poisson distribution, I have to construct the probability function for which I need m. So how I can calculate m now? Here no number of trials or probability of any occurrence is given. So instead the probability itself for x taking 0 is given. So with that data, let me first take m. So taking a note of the probability given in the data, that is e power minus 3. So we can consider it is a Poisson distribution. Now so here for Poisson distribution, we know that probability function is m power x exponential minus m by x factorial, where x denotes in this problem committing a mistake. Correct? So now the first line that gives committing 0 mistake with the probability exponential minus 3. So that means by data we can say P of x equal to 0 is e power minus 3. But actually if at all I want to find for probability x equal to 0, so how it, if I substitute here, it will give m power 0 by 0 factorial, that is 1 into e power minus m. So that means by data we have probability of x equal to 0 is exponential minus 3. By this probability function x equal to 0, the probability is exponential minus m. So this we can compare. So exponential minus m is equal to exponential minus 3. So by indices law, since the bases are same, the index must be equal to same. Minus m equal to minus 3 means m equal to 3. So we get m equal to 3 here. So once we got m equal to 3 or mean, then I can substitute back here. That gives the probability function whose mean is 3, means 3 power x exponential minus 3 by x factorial. So this is how we can calculate m. Now I have to take these problems, that is a broadcaster commits no mistakes, sorry, 2 mistakes, more than 3 mistakes, at most 3 mistakes. So what is that probability of committing only 2 mistakes means? Only 2, exactly 2, that is P of 2. Substitute here 3 square exponential minus 3 by 2 factorial gives 0.2240. The next is more than 3 mistakes. Probability of committing more than 3 mistakes means P of x greater than 3. More than, not more than or equal to, more than 3, greater than 3, which is the complement of 1 minus probability of x less than or equal to 3. The complement of x less than or equal to 3. So I can write it as 1 minus probability of x less than or equal to 3. So this gives now 1 minus P of 0 plus P of 1 plus P of 2 plus P of 3, where probability function we know that it is 3 power x exponential minus 3 by x factorial, where exponential minus 3 throughout constant, I can take it out. So 1 minus e power minus 3, when x equal to 0, your m power x by x factorial, m power 0 by 0 factorial, that is 1. When x equal to 1, m power 1 by 1 factorial, that is 3 power 1, 3 power 1 by 1 factorial, that is 3, because m is 3 here. So when x equal to 2, that is 3 square by 2 factorial, that is 9 by 2, plus when x equal to 3, 3 cube by 3 factorial, that 27 by 6. Simplify this, that gives 1 minus exponential minus 3 times 1 plus 3 plus 9 by 2 plus 27 by 6 gives 0.3528. Give this to Calci, we'll get the answer 0.3528. Now what about the next? Now probability of committing at most 3 mistakes. So maximum is 3, that means less than or equal to. So probability of x less than or equal to 3. So I have here actually less than or equal to 3 means 0, 1, 2, 3, 4 values. Or I can take, now already we have taken probability of x greater than 3. So certainly x less than or equal to 3 is the complement of this. So 1 minus probability of x greater than 3. So I have the answer 1 minus 0.3528, that is equal to 0.6472. Or if you want, you can take the direct way also, which gives the same answer 0.6472. But we have to substitute all these data So when x equal to 0, what is the answer? That is exponential minus 3 is common anyhow. So m power x by x factorial for x equal to 0, 1, 2, 3 substitute, we will get this. So simplifies to 0.6472. Next, problem number 6. If a random variable has Poisson distribution such that p of 1 equal to p of 2, find mean of the distribution, and second one is probability of x taking 4. Now again here also for Poisson distribution, I want m first. For finding m, the data here it is given probability of x taking 1 is equal to probability of x equal to 2. So we know that for Poisson distribution, the probability function p of x is m power x exponential minus m by x factorial. And by data, that is p of 1 equal to p of 2. So that means if I substitute here x equal to 1 and 2, we'll get m e power minus m by 1 factorial is equal to, when x equal to 2, m square by 2 factorial exponential minus m, which simplifies to, I can cancel exponential minus m on both sides. So m equal to m square by 2 or m equal to 2. M on both sides it cancels. So m by 2 is equal to 1 means m equal to 2. So we got mean. So thereby the mean of the Poisson distribution is m equal to 2. The second question, now I want probability of x taking 4, that is p of 4. Substitute x equal to 4 here, where m is already got 2. So 2 power 4 exponential minus 2 by 4 factorial, which simplifies to 0.0902. Problem number 7. Fit a Poisson distribution for the following data and calculate the theoretical frequencies. The data is given for x varying from 0 to 4 and corresponding frequencies are given. This is observed frequency. When x equal to 0, 122, when x equal to 160, when x equal to 15, when x equal to 3, 2, when x equal to 4, it is 1. Now if at all I want to find a theoretical frequencies by fitting into Poisson distribution, so that means I need m for probability function. So how to calculate m here? So if I observe this, it comes to be 200. So that means the given data is out of 200. So what is the number, observed number, by taking x as 0, 1, 2, etc. given? So I can find the average for this data, x bar, that is summation f into x by summation f. So which is nothing but m for the Poisson distribution. Since we know that for Poisson distribution, mean mu is equal to m. So let me first calculate the average. So mu is equal to, that is x bar is equal to summation fx by summation f. That is sum of the product of these data. So 0 into 122 plus 1 into 60 plus 2 into 15 plus 3 into 2 plus 4 into 1, which gives 100, divided by summation of f is 200. So 0.5 is the average. So that means for Poisson distribution, mu is nothing but m, so which is 0.5. So thereby the probability function p of x is 0.5 power x exponential minus 0.5 by x factorial. Now since I want here theoretical frequencies means expected number out of 200. So let me take it as f of x by multiplying this with 200. So what is that? F of x is equal to 200 times p of x. So 200 into 0.5 power x exponential minus 0.5 by x factorial. Since exponential minus 0.5 is 0.6065, multiply that with 200. So it gives 121.3 into exponential minus 0.5 by x factorial. Now I can get the frequencies corresponding to x equal to 0, 1, 2, 3, 4. So we get theoretical frequencies as follows. So probability, even if you want, you can find the probability of x taking 0, 1, 2, 3, 4. Thereby we can get the theoretical frequencies. Or we can get theoretical frequencies directly by using this 120, which simplifies to 121.3 into exponential minus 0.5 by x factorial. Now here if at all I take probability when x equal to 0, 1, 2, 3, 4, my probability function is defined as 0.6065 into 0.5 power x by x factorial, which comes to be this. Once if you find this, then you have to multiply this with the 200, so that you will get the theoretical frequencies. Or else directly you can get this formula. So substitute x here, so we'll get the answer which turns out to be 121, 61, 15, 3, 0. Now, what is the given data, that is the observed data is here. So if you observe that the theoretical frequencies is very close to the observed frequencies. So we have taken two distributions on discrete probability distribution, one binomial, another is Poisson. So we need to remember here the binomial distribution is characterized with the two things, the probability of success and the number of trials, P and N. But Poisson distribution is characterized with the mean number of success, that is M. So that means for binomial distribution, P of x depends on two parameters, N and P, and Poisson distribution probability function depends on one parameter, M. And the probability function for binomial is P of x equal to NCx P power x q power n minus x, where n is the total number of trial, P is the probability of success, thereby q we can get immediately 1 minus P, probability of failure is q. Now for Poisson distribution, P of x, the probability function is m power x exponential minus m by x factorial, where m is mean number of success. Thank you. That's all for this video 3. In next video, we'll move on to continuous probability distribution, where we take exponential distribution.